In this presentation, I'm going to clarify what all of these statistically significant associations do not mean. This is arguably the most important concept that you'll take away from the course, so it deserves its own presentation. I'm going to call this presentation the third variable problem. In quantitative research, there are generally two types of studies. In an experiment, investigators apply treatments to the observations and then observe the effect the treatments may have had. In an observational study, investigators simply observe subjects or participants and measure variables of interest without assigning treatments. So despite the fact that we have imposed a causal model on our research question by selecting an explanatory and response variable, in fact, because we're working with observational data, we cannot test causality. Although we found a significant association between major depression and nicotine dependence, and decided that major depression was an explanatory variable and nicotine dependence a response variable, this simply reflects the causal model that we've imposed. It's possible that major depression causes nicotine dependence. But it's also possible that nicotine dependence causes major depression. But even if we were able to establish that major depression develops before nicotine dependence, thereby discounting the opposite causal relationship, even then we cannot say that the association is causal, because there is always the possibility of the influence of a third variable. For example, maybe major depression and nicotine dependence are associated through alcohol use. Maybe it's folks that use alcohol that are more likely to be depressed and also more likely to smoke and become nicotine dependent. Or maybe a third variable explaining the association between major depression and nicotine dependence is stress. High rates of stress may influence the development of both depression and nicotine dependence. Or maybe it's genetic propensity, that there's some sort of underlying genetic cause for both major depression and nicotine dependence. There are, of course, many other possibilities, but the bottom line is that you cannot interpret a significant association based on observational data as a cause and effect relationship. In observational research, like what we have been conducting, causality can be a bit slippery to pin down. What I want to show you now is a great clip from an old video series supported by the Annenberg Foundation. The video series is called Against All Odds, Inside Statistics, and this clip shows that causality is one of many possible explanations for the significant associations that we observe. It also reviews how more convincing evidence can be gathered.
It's a little-known bit of beach trivia that ice cream sales are positively associated with the number of drownings. One possible explanation is you should have listened to your mother. Eating before you swim could have grave consequences. Another, more ghoulish explanation is that people on the beach gobble up all the ice cream in sight to console themselves when someone drowns. But there's a better explanation. Both ice cream sales and drownings are showing a common response to a third factor: temperature. On a hot day, more people go to the beach, more ice cream is sold, and more people drown, simply because there are more swimmers. In 1974, Congress lowered the national speed limit to 55 miles per hour. The following year, traffic fatalities decreased by 20%. Can we say that lower speeds reduced the number of deaths? The change in the national speed limit was a result of the Mideast oil embargo. But the gas shortage also meant that people were not driving as often or as far as they had before. These factors were confounded or tangled up with the lower speed limit. So it's impossible to distinguish just one cause of reduced highway carnage. The population of Louisiana has been increasing steadily since 1970. At the same time, the state's land mass is decreasing at the rate of 17.5 square miles a year. Is the extra weight causing the state to sink into oblivion? Hardly. The association is purely coincidental. People move for job opportunities and other personal reasons. Shore areas sink because of geological processes. The two have nothing to do with each other.
Association doesn't necessarily imply causation. The best way to make a case for causation is to conduct an experiment. An experiment allows for a direct test. In a laboratory, for example, we can study directly the effect of mixing one chemical with another. That's the basis on which physical scientists say they understand how one thing causes another. But in the world outside the laboratory, in the realm of politics and economics and people's lives, experiments are much more difficult to conduct. Say it's 50 years ago, and you're an eager experimenter with a startling hypothesis. You think that smoking might cause lung cancer. You go to a nearby nursery and choose newborns to be randomly split into two groups. You control the behavior of both groups. Half the infants are forced to smoke. The others you install in an identical environment, but you forbid them to smoke. Then you go off to write some new grant proposals. 30 years later, you show up again and compare the rates of lung cancer in the two groups. You could be confident that whatever differences exist between the two groups are due to smoking. While it's quite common to use human subjects in experiments, obviously the one I just described is unfeasible and unethical. And yet, today we know there's strong evidence that smoking causes cancer. Cigarette packages even say so. But how do we know it? What's our evidence that causation is the proper explanation for this association? The answer to those questions is a fascinating chapter in the history of biostatistical research.
Smoke, smoke, smoke that cigarette. Puff, 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 and if you smoke yourself to death. Tell St. Peter at the Golden Gate that you hate to make him wait, but you just gotta have another cigarette.
Cigarette smoking became increasingly popular in America after World War I, when cigarettes were handed out to soldiers as a way to boost morale. Per capita consumption rose from 49 cigarettes in 1900 to 611 cigarettes in 1920. But along with a rise in smoking came a disturbing rise in the lung cancer rates and some early warnings from a handful of doctors.
My observations were on the living subject of the patients who had been smoking and who had not been smoking, to see the difference in the appearance and the behavior and the texture of that lung, and then to correlate the medical history of their smoking history.
As a young lung surgeon in the 1930s, Dr. Overholt had noticed that his non-smoking surgery patients had a higher survival rate and a quicker recovery rate than the smokers. He tried to get other doctors to encourage their patients to quit.
A good share of the doctors were smokers. They didn't believe this, and it was very difficult to convince people that this was doing damage to them because they felt that they were getting pleasure from smoking.
During the 30s and 40s, the popularity of cigarette smoking soared as a new image of the smoker took hold. Sophisticated, glamorous, fun-loving, independent. Little thought was given to the risk. But in the early 40s, new studies sounded a louder alarm on the danger of smoking. One of the earliest and most compelling of these studies was conducted by Ernst Winder and his teacher, Everts Graham.
Then in my junior year in medical school, I developed a questionnaire. I began to ask lung cancer patients about their smoking and other habits, and I then did controls, and it was quite apparent that lung cancer patients smoked much more than the controls, and that, in fact, lung cancer in those that never smoked was quite a rare disease.
Dr. Winder, then a student at St. Louis under Dr. Everts Graham, came to me and he said, Camel cigarettes cause cancer of the lung. I couldn't believe it. And you see what you look for, and you look for what you know, and it never occurred to me that cigarettes caused cancer. So we went to see my patients, and at that time I had quite a large practice. We discovered to our amazement that patients who had cancer of the lung were 17 times to 1 as apt to be 2-pack-a-day smokers. So here was a fact trying to tell us something.
This technique was called a retrospective study. It started with people with lung cancer and then looked back retrospectively to see what their smoking habits were. Doctors Winder and Graham then correlated smoking habits and incidence of lung cancer, a method not without its statistical pitfalls.
We are only looking at statistical correlation. We're looking at it in the crudest possible way because we don't have a defined sample from a defined population. We don't have a clear way to measure differential rates of disease or of smoking because we have targets of opportunity in terms of the people that happen to have lung cancer and be in that hospital. And so we can go only so far with a retrospective study and no further.
Doctors Hammond and Horn of the American Cancer Society conducted one of the first prospective studies on smoking. While retrospective studies started with lung cancer patients and worked backwards, prospective studies started with healthy people, smokers and non-smokers, and then followed them forward in time to see which ones developed lung cancer. About 200,000 people were given a smoking questionnaire and then followed for 4 years. The death rates and cause of death for smokers and non-smokers were compared.
The preliminary study published in 1954 caused quite a sensation. It was the largest study on smoking that had been done. It was the first prospective study that had been published, and it showed that people who smoke cigarettes have a lung cancer rate 10 times as high as people who never smoke, and that the risk goes up proportionately according to the amount and number of cigarettes that people smoke per day.
This high correlation was consistent with the findings of the retrospective studies, but there was still disagreement about how to explain this correlation.
There is a set of third variables that is accounting for this correlation between smoking and lung cancer. This kind of thing is not at all uncommon. There are many examples in the statistical literature where two variables are highly correlated with one another, and yet one does not cause the other.
To tackle the problem of confounding variables and common response variables, Doctors Hammond and Horn designed a follow-up study of 1 million people. The smokers and non-smokers were matched on such variables as age, geography, and occupation. The goal was to make smoking habits the only significant difference between the two groups.
And we matched them on 19 different variables, so they were as alike as we could make it. And when we finished this analysis, the death rate of the smokers was higher than the death rate of the non-smokers.
Even though the two groups were as similar as possible, they were not identical. What if smokers differed genetically from non-smokers in a way that both caused them to smoke and caused them to get lung cancer? This objection was stated most forcefully by Sir Ronald Fisher, known to many as the father of modern statistics. Without a controlled experiment, he argued, there was no way to know whether the lung cancer was due to smoking or to another uncontrolled variable. So despite the accumulating evidence from dozens of prospective and retrospective studies, for many scientists and statisticians, the label of causation was still premature.
Each science has its limitation. There's no question about that smoking and lung cancer, the evidence comes from human study, that there is a strong association. However, we like to know more about the disease and how it reacts and how it works, which questions epidemiology never can answer.
But lab studies can answer these questions. Throughout the 50s and 60s, compelling corroborating evidence was being gathered in biochemical and animal studies. Dr. Winder was among the first to demonstrate the presence of carcinogens in tobacco smoke by painting tar on mouse skin and rabbit ears. Cancerous tumors developed.
This didn't prove in itself that cigarette smoking causes lung cancer in humans. That we had already established in our human studies. This was just confirmatory, namely that there are carcinogens in tobacco tar that are producing cancer in the skin of mice.
Another aspect of the prospective studies that was confirmed in the lab was the dose-response relationship. By exposing hamsters to cigarette smoke, it was possible to determine how the number of cigarettes smoked is related to the incidence of lung cancer.
Animal studies as well as epidemiological study very clear shown a dose response. The more you smoke, the higher is your risk.
So you have carcinogen tobacco smoke. It is proved to be carcinogenic to animal tissue. It is highly correlated in retrospective and prospective studies in respect to cancer of the lung in humans, and that was more than sufficient to establish tobacco smoke as a cause of lung cancer and subsequently other cancers in humans.
So while we have imposed a causal model on the research question that we have been asking, because we are working with observational data, we cannot provide direct evidence for causation. Bottom line is that a significant association cannot be interpreted as a cause and effect relationship based on observational data. As we saw in the video, more convincing evidence needs to be collected. That doesn't, of course, stop us from actually testing our ideas about causation, as we've been doing in this course. But science is iterative. We generate hypotheses, consider expected results and observations, examine actual results and observations, and then interpret our data, evaluating whether it supports our hypothesis, opposes our hypothesis, inspires a new revised hypothesis, or helps us to revise our assumptions. I encourage you to keep these ideas in mind, not only as you conduct your own research, but also as you move through the world as a consumer of quantitative research findings. That's all for now.